reaction. This reaction was developed by a British chemist. His name was Robert Robinson. And Robert Robinson won the Nobel Prize for this work. And at one point in England, if you got a Nobel Prize, you got knighted. So a long time ago, you only got knighted if you did something good, not a musician, nothing of that sort. So his name is referred to as Sir Robert Robinson. But he did really wonderful work, and he was able to develop methodology to make a lot of fuse systems. So recognize here, I have a cyclohexanone ring. And in this methodology that I'm about to share with you, I'm able to take a 6-member ring and fuse a second 6-member ring from it. Okay? And in fact, this method is also an effective method to make a lot of the steroidal compounds that, that have been around for some time. Okay? So testosterone, estrone, progesterone, a lot of this stuff that led to women having birth control pills was really developed during that time of the 50s and 60s. And a lot of it was developed through this type of methodology. What's cool about the Robinson annulation is it takes the two reactions that we just learned. It takes the Michael reaction, which is from this chapter, and then it employs the aldol condensation that we just learned in chapter 23. So recognize what I have here in this system is I have a dicarbonyl system. So obviously with base, that's going to be my most acidic proton. And here is what I just gone over for the most big part of today's lecture. This is a microacceptor. So the microacceptor, again, that's my carbon. That's going to be the electrophilic center. And that's going to be my nucleophile that's going to be generated by abstraction of that proton. So if I remove this proton and generate that enolate, that nucleophile will attack this beta position to give me this guy. Okay? Now recognize if I take this key methyl position here, okay, and if I take this methyl position and deprotonate it, notice I have 1, 2, 3, 4, 5, 6. I would make a 6-member ring. Okay? Now notice that I also have an alpha position here. If I deprotonated this, the best I could do is make a ring system that's 1, 2, 3, 4. Recognize 4-member rings are not very stable. 6-member rings, again, are always thermodynamically stable. So when you have the possibility of making 6 and 5-member rings, it will do so. So the fact that I deprotonate this position will permit me to do an aldol condensation in which I remove this electron and push it here, and then that oxygen, I form a beta hydroxy system. Under those reaction conditions, I will lose water through an E1CB mechanism and form this system here. Okay? Now, recognize something that's bitching about this. So I'm starting off with this molecule here. I'm doing a Michael addition to get this adduct. I do an intramolecular aldol condensation. What can you tell me about this product here?
You conjugate it?
It's another Michael addition, right? So I could repeat this process. The fact of the matter is, after this reaction, I have a Michael addition. I can start doing the same process over and over again and make rings after rings on the system.
Oh, wow. Cool.
Okay?
Okay, yeah.
So it's really kind of cool because you have this repeating system, right? You start off with a Michael, you end up with a Michael. So what if you employed another system here and continue on? Really cool stuff, guys. Really cool stuff. Okay? So again, I'm not going to explain all the mechanisms to you because again, it's just a review of what we learned both today and yesterday. But I'll be candid with you guys. If I gave you guys something about Robinson annulation, it permits me to test you guys whether or not you understand both the Michael reaction mechanism as well as the aldol reaction mechanism. Okay, it's a big hint.
That is super cool. Thank you. I really like this reaction too, and it's very neat.
Okay, so let's see how it's used. So I'm not going to do this for you today because of time, but I encourage you guys to do this after we leave today. Okay, so this will be part of my problem set, my additional problems. Try doing this, and tomorrow morning, I'll show you the answer to this. We'll go over the answer, okay? But notice, again, you can see the similarity to what I previously did. Here's the microreaction. That's going to be my electrophile. So now the question is, this has to be my nucleophile. Which is the most acidic proton? This guy here. This is a beta ketoester, right? So that will make this microadduct. And then formally after that, you basically do an aldo reaction where, again, I'm going to count. How do I make a 6-member ring? I'm going to deprotonate this position because this, if I deprotonate here, it's going to make a 1, 2, 3, 4, 5, 6 position. Please recognize that when you do these aldo condensation reactions, particularly in ring systems, it doesn't stop at the beta hydroxy. It goes all the way to the conjugated species. Okay? What time is it? Okay. I'm going to let you, I know I've been taking a little bit long time, so I'm going to stop here for today.